Hello, and welcome to the first part of a three-part video series on the synthesis of alum crystals. My name is Christopher Velota, and I am looking forward to explaining the intricate chemical processes involved in this experiment. This experiment was actually divided into three parts as seen below: the actual synthesis of the alum, rinsing the alum, and recrystallizing the alum. But we will be focusing on the actual synthesis of the alum. In the first step of alum synthesis, approximately 1 gram of aluminum foil was dissolved in 50 milliliters of potassium hydroxide, producing aluminate ions and hydrogen gas. This solution was vacuum filtrated, leaving behind a clear, colorless solution of potassium and aluminate ions, as well as any unreacted potassium hydroxide. Both the full and net ionic equations are shown. Following this, 25 milliliters of sulfuric acid was added to the solution. However, only about half of the sulfuric acid will be added in this step. This is because the aluminate solution initially reacts with the sulfuric acid to produce a thick, white, jelly-like precipitate known as aluminum hydroxide. This aluminum hydroxide is insoluble, as almost all hydroxide salts are, but will dissolve upon the further addition of the remaining sulfuric acid, as seen in the reaction below. Soluble potassium, sulfate, and most importantly aluminum ions are produced in this reaction. Sometimes, as occurred in our experiment, the aluminum hydroxide did not dissolve upon the addition of the remaining sulfuric acid. In this case, heat was applied for about 10 minutes, and then a further 10 milliliters of sulfuric acid was added before all of the aluminum hydroxide eventually dissolved. The final step of this crystal alum synthesis involved placing the solution in an ice bath. This was done because alum crystals are soluble at room temperature. Decreasing the temperature would decrease the solubility, forcing crystals to precipitate out of the solution. And indeed, after approximately 10 to 15 minutes of cooling, small alum crystals were observed at the bottom of the flask. As mentioned before, part 2 of the experiment simply involved cleaning the crystals with an ethanol water mixture to remove any contaminants. It also involved separating the crystals by vacuum filtration. And finally, part 3 of this experiment involved making 20 milliliters of a saturated alum solution, producing this vial of saturated alum solution. As you can see from this picture, alum crystals have yet to form. Perhaps more time is still necessary for the water to evaporate. I will continue to keep an eye on the solution for the days to come. In this experiment, we used a slow cooling technique and are now using a slow evaporation technique to form crystals. However, a liquid-liquid or liquid layering technique could also be used to form different types of crystals. In this process, a separate liquid solvent is carefully layered on top of a solvent with the desired dissolved crystal compound. Both of these solvents must have different densities in order for the liquid boundaries between them to remain distinct. As seen in the figure, solvent 2 slowly diffuses into solvent 1, which decreases the solubility of solvent 1. As we have learned from this experiment, decreasing the solubility of a saturated solution will force crystals to precipitate. This technique requires a lot of skill and precision and is often used in microscale crystallizations. For this reason, sodium chloride crystals would best be made by using a slow evaporation technique similar to the one we are currently using for the alum crystals. To put it simply, NaCl would be dissolved in nearly boiling water until the solution was completely saturated. Then this solution would be placed in a container and be left alone for several days. As the solution evaporates, crystals would begin to form on the edges of the vial. I hope you enjoyed this video and thanks for watching.